1 second. Okay. So again, thank you, Dr. Wang, for allowing me to have this opportunity. So the intent of this presentation I plan to do today is to essentially provide basic information about the research we're trying to do, and also provide some more insight into the specific statistical areas that I am researching in regarding the 1 hertz and 10 hertz heat flux frequencies. So just as an introduction, this is rather elementary knowledge, if you will, but obviously we have greenhouse gases that cause a greenhouse effect that which is essentially the process by which uh, in which you have warming from the planet's surface, and it creates a temperature above what it would be without the atmosphere, and essentially it traps all of the heat. And this is largely caused by water vapor, carbon dioxide, methane, nitrous oxides, and ozone. Um, and so because of that, all of these greenhouse gases, you have a lot of trapped heat, which we can see through this next diagram here. And so as you can see from it, uh, some of the heat will be like trapped in the atmosphere and increase the overall global temperature. And yes, so as an introduction, so at our current rate, our temperature could definitely increase by 2 degrees Celsius, which the United Nations considers as the upper limit to avoid dangerous levels by 2036. And so in order to measure these heat fluxes, we use the eddy covariance technique. And basically it's a measurement technique that calculates vertical turbulent fluxes within the atmospheric boundary layers. And with that, you can divide it further into 1 hertz and 10 hertz of greenhouse gas fluxes that you can collect that from the eddy covariance. And obviously, as I've demonstrated in the past couple of weeks, that's mostly what I've been focusing on, the 1 hertz and 10 hertz, and and interchanging them as independent and dependent variables, or if you will, the regressor and the regressand. So through all of this research I'm doing, I am essentially using each frequency as either a regressor or a regressand, so that I can create a least squares regression line, so that we can better understand the relationship between the 1 hertz and the 10 hertz frequency. And so yes. And again, if you have any questions or comments, please let me know. You can just speak up. And so obviously this is the methodology here, where we have the 10 hertz as the regressand and the 1 hertz as the regressor. And frankly, these are very just simple linear equations. As we see here, you could equate this very simply to like y is equal to mx plus b, or in this situation, b minus mx, but yes. And so in order to perform all of this research, I largely used Excel spreadsheets. And moving on to the data portion, I've already discussed this, but it doesn't hurt to reiterate. For the most part, we've seen this very common trend where the 10 hertz typically has a higher, steeper slope than the 1 hertz. And we determined this by our control, if you will, of the 45-degree line here. But as we've seen in numerous circumstances, there have been discrepancies. So this one wouldn't necessarily be, as you can see here, this is actually a rather good reading because you can see the 1 hertz and the 10 hertz, they follow each other rather well as you go through the tracing of the heat flux. Uh, but occasionally there are instances where, particularly with the 10 hertz, where it acts a little abnormally, if you will, where it crosses the 45-degree line and has an exceptionally steep slope. In fact, if you possibly extended this further, one could possibly surmise that the 10 hertz crosses the 1 hertz, which is rather abnormal. And as you can see here, the 10 hertz and the 1 hertz, they seem to have not necessarily inverted their position, but their slopes are very low. And I believe this does go to the issue we may have had with some of the readings, whether or not that is a mechanical issue with the equipment. Frankly, I'm not too sure, but these readings seemed unusual to say the least. So definitely looking into that further will be important to do. And if we just simply look at the graph here with the heat flux, you can see that the 10 hertz does not have as near high of peaks or troughs as the 1 hertz. So that definitely demonstrates that there are some issues, particularly,
Again,
yes.
I mentioned last time, this data set may not give you the correct variables.
Yes.
Looks to me although labeled 1 hertz, 10 hertz, but that's not what 1 hertz, 10 hertz at the same level. Instead, it is the same hertz measurement, but one is below, one is above the canopy top. That's what it
Oh,
looks
yes,
like
that's
to
true.
me.
That could be. I guess the question I had is why would there be such a difference though with the canopy top?
Well, canopy is kind of insulator.
I see.
Below the canopy, they will reduce the fluxes substantially.
Okay. So would the canopies would they trap heat or prevent heat from coming in?
Well, they prevent exchange process.
Okay. So both essentially, right?
It reduces how fast the heat can move in and out.
I see. Okay. That definitely makes sense. So that's a possibility that could explain many of these readings. It likely has to do with the canopy.
Especially this one.
Yeah,
Yeah.
yes, that would make sense.
Yeah.
So for this one in particular, do you believe that it would be um that both of the readings took place under the canopy or
No, I think here what's labeled 1 hertz
mm-hmm.
is the flux above the canopy.
I see.
The one labeled 10 hertz is the same flux below the canopy.
Oh, I see. I see. That makes sense.
Yeah, since they have the same diurnal cycle, but a different magnitude.
Okay. So let's see.
Yeah, that again looks like a 10 hertz versus 1 hertz thing.
Mm-hmm. Yes. So as I've explained before, I compared the 1 hertz and 10 hertz LSRLs, if you will, with a 45-degree line, which I used as control, which is a control.
Mhm.
And so moving forward, I plan to not only look into heat flux, but also look into greenhouse gases as linear regression to see if we can establish some sort of trend, possibly, likely not a correlation, but some sort of strong relationship between the greenhouse gases and the heat flux. Although I believe as like empirical evidence from before has mentioned that there is a relationship between an increase in greenhouse gases and heat flux. But again, I would definitely like to study that a bit further to solidify that claim, if you will.
Okay, good idea. In fact, uh, CO2 flux on large scale has been rising steadily, as you know.
Yes.
But if you look at the 50 years, that's pretty obvious.
Yes.
But I doubt the sensible efflux has that trend, if at all. And so there are two very different processes. Even though you look at CO2 flux and water vapor flux, CO2 flux, you see obvious trend. That's from the Mauna Loa in Hawaii. They show the increasing CO2 concentration of the atmosphere. That implies the CO2 flux is increasing as well.
Yes.
But you don't see that in the water vapor flux, at least not that obviously, since the water vapor content of the over the last 50 years it does not increase that much.
Okay.
It's interesting if you can look at the longer term, but use other data set, but not the data set from this site. So we only have a data set for 3 years or so, but to look at the trend, you want to look at much longer record.
Definitely. That is true. So yes. Thank you so much, Dr. Wang. This has
No problem.
been a tremendous opportunity. Okay. Thank you.
If you are interested, you can search online quickly. You'll find the CO2 record. You can find it easily online.
Yes, that's true. I will make sure to do that.
It's available, to everyone.
Okay. Thank you.